All right, so we're finishing off the ones we didn't get to finish in class. Discuss the difference in the type of energy present as a child climbs to the top of a slide, stands at the top, and slides down. So let's separate that. We're going to separate into climb, then we're going to have stand at the top, and then we're going to go slide. Okay, so those are three kind of things. So as the child is climbing, right, they're doing something. Anytime you are doing something, that is a kinetic energy. Kinetic, kinetic energy. And so as the child is climbing, right, the more they climb, the more they're converting that kinetic energy into potential energy. So then we end up, when they're standing at the top of that slide, they then have potential energy. And that potential energy is then going to get converted back to kinetic as they slide down. Okay. All right, 1.46. A moderate walk burns 225 calories per hour. Calculate the number of joules burned by this activity. So you have to have a conversion factor one. You need to know that 1 calorie, C-A-L, 1 calorie, is equal to 4.184 joules. O-U-L-E-S. Okay, so we know we have 225 calories being burned per hour. So if we start with 225 calories, 225, now I'm going to call this the big C. The big C is calories that we find in food, right? Whereas the small c is calories in energy. So this is our energy calorie, whereas we have in food the big C. One big C is the same thing as 1,000 calories, right? So the scientific one is the one that we're going to spell out. This is the one that you should be using, but the nutritional industry has its own calorie that we just call the big C. So we know that we're burning 225 big C calories per 1 hour, okay? So I'm going to start my fence post because I know I'm going to have to convert my units. So I need to convert my big C. I need to get that out because I'm trying to get to joules. So I put my big C on the bottom, and I'm going to put what else is in that conversion right here on the top. So I know that's 1,000 little c, or calories, right? Now I know that I have one calorie for every 4.184 joules. Okay, so my big C calories cancel, my calories cancel, and I'm left with joules per hour. So calculate number of joules burned by this activity, and we did it in 1 hour. So what is the total? So you multiply 225 times 1,000 times 4.18, and what you should get is 941,400 joules. But think about our significant figures. We have 3, so we have to round that to 941,000 joules, right? So that gives us our total number. All right, 1.48, which has a higher specific heat, water or salt water? So if you go look in your textbook, they have a table. And in that table, you'll see that water has a specific heat of 1.00 calories per gram degrees Celsius, whereas salt has a specific heat of 0.21 calories per grams degrees Celsius. So because salt has a lower specific heat than water, when we mix the two, the salt water is now going to have a lower specific heat, right? Because we're basically adding these two components together. One has a high specific heat, one has a low. So then the mixture is going to be somewhere in between. So then salt water will have a specific heat, I'm just going to abbreviate, that is between water and salt. So which has a higher specific heat? Our answer is that that water has. So we're going to say, so water has a higher specific heat. H-E-A-T, whoa, than salt water. Okay. All right, 1.50, indicate if each of the following describes a solid, a liquid, or gas. So A, state of matter has a definite volume, but takes the shape of its container. This one has to be a liquid. Okay. B, the particles in the state of matter are so far apart they do not interact with one another. That's the farthest, and that is gas. All right, measuring matter. Okay, 1.52, consider the following measurements determined for a known volume of 10 milliliters. All right, so we have two experiments that were done. One experiment where we measured this volume with a graduated cylinder, and a graduated cylinder kind of looks like this, and it's got a base and it's marked, right? Its volume is marked. And so you look at the meniscus and all of this is fluid, right? And so you would look and you would say, okay, that's 10 milliliters of water. Okay. So you could either measure it with a graduated cylinder, that's experiment one, or you measure it with a beaker. And a beaker is a much larger container and it has fewer volume markings. So which set of measurements is more precise? Remember what precision and accuracy are. Remember that, let's see, if we have something that is more precise, that is going to be something that is closer to the accepted value. Okay, so which one is more precise? Which ones got me an answer that were closer to the actual value? And so if we look at these, what we're going to see is that we're trying to get to 10. So if you add these up and divide by 3, what you're going to get is 10 milliliters, right? So 10 plus 9.5 plus 10.5 divided by 3 is going to give us 10. So these measurements are pretty gosh darn precise, right? Look at your volumes measured with the beaker. If we took our volumes measured with the beaker and we do that same thing, we do 12 plus 8 plus 9, and we divide it by 3, what we're going to get is something like 9.6 repeating decimal. So which one's more precise is going to be our graduated cylinder. And which measurement is going to be more accurate? Now this is different. Accurate is how close measurements are to all the other measurements. Well, these are all pretty close here with our graduated cylinder. Whereas here we have a range from 12 to 8. That's a huge range of values. And so that's not very accurate. So our accurate ones are also the graduated cylinder. AR or ER? I don't remember. So which measuring device for volume is more accurate? Which one do you want to be using? Well, I want to get my answer right more of the time, so I'm going to use a graduated cylinder, even though I can't spell it. All right, let's see, 1.54. A mother is to give her child 10 cc's of medicine every 6 hours. Unfortunately, she lost the syringe provided with the liquid medicine. This happens all the time. She calls your clinic for help. How much medicine in teaspoons can you instruct her to give the child per dose and per day? This is very common, all right? So what you need to know is you need to know a conversion. You need to be able to go back and forth between cc's and teaspoons, right? So what I can tell you is, I'll give you a conversion. I know that 5 cc's is equal to 1 teaspoon, okay? So if she was told to give 10 cc's of medicine every 6 hours, so can I change cc's to teaspoons, and then we can calculate things from there. So 10 cc's, I know there are 5 cc's in 1 teaspoon. So now I know that the doctor prescribed her 2 teaspoons, right? Because 10 divided by 5 is 2. So my cc's canceled and I'm left with teaspoons. So she was told to give 2 teaspoons per dose, right? Every 6 hours, she was told to give that. So 2 teaspoons, that's our first answer. Now we want to know how much per day. So now this is really 2 teaspoons per 6 hours, but that was our given dose, right? And so we know one dose is 6 hours long, right? Oh, I'm sorry. Why did I write that? It's 2 teaspoons per dose. And so we have in one dose, 6 hours. Then we have, we want to know how many per day. So now I have hours down here. So I know that I have 24 hours in one day. So that gets me the day I want. I can cancel out hours, right? And so now I want to know my doses cancel. 2 times 24 divided by 6, I should get 8 teaspoons per day. Okay, so our first answer was 2 teaspoons per dose, and the last answer was 8 teaspoons per day. All right, 1.56. We have a 38-pound child who is being prescribed a drug for chickenpox and the amount of 80 milligrams per kilogram of body weight per day to be divided into 4 doses. Oh my goodness, right? Each tablet contains 700 milligrams of the medicine. How many tablets should be given per day and per dose? All right, so let's start with what we know. We know that the dose was 80 milligrams. And that 80 milligrams is per kilogram of body weight, right? Every child's going to have a different body weight. And so you need to make sure that you're giving the right amount of drug for however much that child weighs. So you take that dose of 80 milligrams per kilogram and multiply it by the child's weight. So they said the child was 38 pounds. Oh my goodness, I can't do that, right? Because my units don't cancel. So what I have to do is I have to convert from kilograms or from pounds to kilograms. All right, so what I'm going to do is extend this out, and I'm going to say, I know I want to get rid of the pounds. 2.2 pounds are in 1 kilogram. And I think that's a conversion that's on the back of your, in the back of your book. Okay, so I know that that ends up being, right, kilograms cancel, that ends up being 1,381 milligrams, but this is per day, per one day, right? To be divided into 4 doses. All right. Each tablet contains 700 milligrams of medicine. So how many tablets should be given per day? Let's answer that first because we're in days. So I know that I have 700 milligrams in 1 tablet. So my milligrams would cancel. I'm left with tablet per day. So that's a great question. That's 1.97. But can you really do 1.97 of a tablet? No, you're going to round. So you're going to say, that's going to say be 2 tablets. ABLE, 2 tablets per day. So that's my answer to my first question. How many tablets per day? 2 tablets per day. Now the question is, how many per dose? Well, I know that I'm going to give this into 4 doses. So I know, I'm not doing the X, we're doing the fence post. Okay. That in one day, I'm going to have 4 doses, right? So just divide it by 4 and you get 0.5 or half of a tablet per dose. Okay. So you can't give a child the whole thing. So you can get a little pill cutter and you can give them half a tablet per dose. Okay, 1.58. Let's see. A child must take 10 milliliters of see, I don't even pronounce all these. I never prescribe these. But an antibiotic by mouth 2 times a day for 10 days. The solution provided is a 50 milligram per milliliter suspension. How many milligrams will the children have taken when the course of medication is over? All right, so this is a little bit of a long one, right? So we're trying to get to, think about what's your goal. The goal is I need to get to milligrams. So I'm going to kind of highlight that so I kind of know where I'm going. Then all the other numbers are numbers that you're either going to start with or numbers that you're going to use as a conversion. So let's start with, let's kind of highlight the other things that we have. We know we have 10 milliliters of our antibiotic. We know we're taking it by mouth 2 times a day for 10 days. And we have a 50 mg per mil suspension. So let's start with something that only has 1 value to it. Instead of like the 50 milligram per milliliter, let's pick something that has only 1. So we know we need 10 milliliters of the drug. We'll just say drug. So how are we going to give this child this drug? We're going to give this child this drug 2 times per day. Okay. And how long are we going to give it to him? We're going to give it to him for 10 days, right? So our days cancel. Now we're trying to get to how many milligrams, but we're in milliliters. So that's not going to work out. But do we have a conversion that'll convert between volume and mass? And we do. We know that in 1 milliliter, we have 50 milligrams. So here our milliliters cancel and we're left with milligrams. So it should be, if you do your math on this one correctly, you should get 10,000 milligrams for our total, right? Our total treatment. And be careful that you know what the question's looking for. Looks like I skipped 1.59. All right, that's okay, we can do that. A patient gets 2 liters of fluid over 18 hours through an IV. The drop factor is 20 GTT per milliliter. Calculate the drip rate in drops per minute. That's GTT per minute. So what are we given? We're told we have 2 liters over 18 hours. So we're going to go 2.0 liters, that's a point, over 18 hours. All right. Now we want to get that drip rate to drops per minute. And drops is just GTT. I know it looks weird, but it's just drops. All right. So let's get rid of our liters first. So we know liters on the bottom. We're trying to get to drops per minute. Well, we can't go straight from liters to drops. That's really kind of hard. So let's go to something smaller. Let's go to milliliters. So our liters cancel. We're left with milliliters. Well, we know we have 20 drops per milliliter. So in 1 milliliter, I know I have 20 drops, or GTT. Okay, so there. Now I'm in GTT, but I'm in GTT per hour. So now I need to switch and I need to get rid of my hours. So I know that whatever I want to get rid of, I got to put it on the opposite side. So here it's on the bottom. So I'm going to put 1 hour on the top. And I know in 1 hour, I have 60 minutes. So my hours cancel and I am left with 37 GTT, or drops per minute. So that's 2 times 1,000 times 20. Hit enter, divide by 18, hit enter, divide by 60. Okay, how long would it take in hours? This is where we're trying to go. To administer exactly 500 milliliters of fluid through an IV with a drip factor of 30 GTT per ml if the drip rate is 60 GTT per ml. All right, so let's see, we're starting with 500 milliliters of fluid. What are we doing? Well, we got to get rid of milliliters because we're trying to get to actually time, but we don't have anything that's going to get us to time. So we got to get out of milliliters. Milliliters isn't going to work. Here I have a conversion between milliliters and drops. So let's use that. So I know in 1 milliliter, I have 30 GTT, which is drops. Now, I'm still in volume of drops. I need to get to time. Here's a conversion that has drops and time. So I'm going to say in 60 drops per 1 minute. Okay, so now I'm in minutes. That's great. Now I need to get to hours. I know in 60 minutes, I have 1 hour. So that gives me a total of 4.17 hours. Now, the only thing I don't like about this is that every one of the initial values has 1 significant figure. So technically, you'd have to report that as 4 hours. All right, last one. I do believe last one. Yay. A medium-sized carrot weighs 61 grams and contains 6 grams of carbohydrate. What % of the carrot is carbohydrate? So that's 61 grams. That's our carrot, right? And we know we have 6 grams of just carbs. So what you do is you say, you want to know what % of the whole, right? So if we have 6 grams of carbs, that's our part is equal to some % of our whole, which is the 61 grams of carrot. Okay. And so remember, that means we divide by 61, and to make it a %, we multiply by 100. So you should get 9.8% but I'm looking here, we got one significant figure. Ooh, boo-hoo, one significant figure. Rounds to 10%. All right, that's it.